we've been talking about things like dates, strings, integers. Let's look at another example, though, that we've actually seen in an example database, like addresses or locations. So let's say you have a database of business locations, or even just building locations, any building, like residential buildings, commercial buildings, whatever. And for simplicity, let's just say that an address is just an XY coordinate, like it is in Salt Lake. So you know, just 500 east, 200 south, or whatever. Mic went on. Is that better? Yeah. Okay. So let's think about this in terms of the kinds of queries we might want to do on spatial data. So data that represents a location in space. We'll deal with 2D points for simplicity. So you might want to, say, find all fast food within like 1 kilometer of my current location. If you're in some foreign city and you're looking for somewhere to eat. This is exactly what Google or Yelp or something does. Or you might want to find the K nearest somethings. Like find me the K nearest power distribution centers or hospitals or something, where K is some small integer. Or find all locations within some shape, some polygon, like a county. Like find all hospitals within county X, where the county is just some arbitrary polygon that makes up a shape. SQL supports various spatial data types, so we can actually make a point. You could just make 2 columns, you know, X and Y, but you can actually make them into 1 column called a point. And then it can actually support special operations like these. Line string is basically a bunch of points that make up a line, or you know, a jagged line. Polygon is some arbitrary shape defined by something like a bunch of points. So those are the kinds of things that will support this sort of query. A point in 2D could be an address, could be like latitude and longitude. Okay, so let's look at this. Say these are my points. I don't know what they are, but they're just points in 2D, the black dots. And then X is the point of interest. So that's like my location, maybe. Say I want to find the K nearest neighbor. So this is a common problem called KNin. Or I want to find all points within D meters of the point X. So KNin would be, say K is 3. I would want this point, and then probably like that one would be the 3 nearest points. Or if I wanted all points within D meters of X, you know, draw a circle, and pretend that's actually a circle with whatever radius you're interested in, and then any point that lies in that circle is your answer. So how do we do that efficiently? Pretend there are 100 million points. How did I know that? How did I know that this was the closest point to X? We need some kind of data structure, but the point is that regular search trees are not going to work. A regular search tree is assuming a one-dimensional number line, essentially. Things to the left are less than, things to the right are greater than. That's how the search tree is built. So we have to have some one-dimensional definition of less than and greater than to build this tree.
I was just going to ask, is it a KD tree?
Yeah, so you could make something like a KD tree. There are other data structures, basically, that this is not going to work. A B tree is not going to work. A BST is not going to work.
And we can't just use the distance equation over one dimension because...
You can't use the distance equation over one dimension because you don't know what X is at the time of building the data structure. You could do that if you ever only wanted to query for this one point X. Yeah. But you might also be wondering, well, why not just build two data structures, one for like the x dimension and one for the y dimension? So yeah, if you did that, you could find, okay, this is the point that's closest to it in the x dimension. How does that help us determine whether it's the actual closest point? It says nothing about the y dimension. And this would be the closest point in the y dimension. It's just kind of, it doesn't really help. Yeah?
Let's take a line, like find the distance between the 2 points, turn it into a line, find the distance of that line, and show this line.
So find the distance between the point we're interested in and some other point and draw a line. Yeah, that's basically what we want, is like, what is the length of that line? Problem is we don't know we don't know where we're interested in ahead of time. Does that answer your question, or what? Okay, maybe I misunderstood the. You could pre-compute all of these distances if you knew what query point you were interested in, but then that works for me, for my phone. Say this is my GPS coordinates. What about somebody else if they're like over here? Then the answer totally changes. I don't know the distance between this point and all other points. So we will need a different kind of data structure to solve this problem, and let's look into that, but we'll take a break now. So let's think about this problem and try some things. One option is just make a regular 2D grid. So you take the entire space of all of the points and divide it up into some fixed number of divisions in x and y. And then for every point, you just figure out which cell it goes into. So rasterize every point into one of the grid cells, and that's your data structure. Okay, and then, so all of the black stuff is the fixed stuff that's part of the data structure, and then you have your dynamic query X. So the two different questions we might want to ask: everything within a radius and k nearest neighbors. So if we did everything within a radius, this is actually pretty straightforward. You just go out you kind of expand in a square way until your square contains the entire radius. But now you have a square versus a radius, so you have to do some false positive rejection, where this little one that I'm pointing at with the arrow is within the square region that I've searched, but it is not within the actual radius. But it did cut out all of these other dots outside of the blue region, and I didn't have to look at them. Okay? For k nearest neighbors, it could work in the same way. You could do the same sort of algorithm, but the question is, how well will it work? If k is 2, then in this case, then going out by only 1, expand by 1 cell in every direction from the origin, finds the k nearest neighbors. But if k was 3, then I would suddenly have to examine all of those other cells, expanding out 1 in each direction. And I don't know which one of them is actually the closest. I would have to compare their distances for every single one. And that problem gets even worse if your grid looks more like this. So how well does a grid handle empty space? You have all these entries in your data structure that hold no information. So for k nearest neighbors, let's look at this. What if k is 1? It's the smallest k we could even use in KNin. I have to go out 2 levels from the origin. If k is greater than 1, I have to go out 3 levels. And then I'm basically looking at every single thing. And the data structure has not helped at all. So in this example, if k is greater than 1, I have to search the blue, then the green, then the orange, and all of the points in there I have to do a distance comparison with the x. So how does the grid handle empty space? Very poorly, and that's why they're not really used to solve this problem. So the better solution, big surprise, involves a tree. It's a different kind of tree. We're going to look at a very dumbed down version of it. So the real data structure that most DBMS use is called an R tree. We're going to look at kind of the ideas of an R tree, but it won't actually be an R tree because we're making a lot of simplifying assumptions. Because first you just kind of have to get the basic concept of what it's doing, and then it gets a little more complicated to do things like optimizing for page access, like a B tree does. You want the nodes to be page sized. We're also going to ignore insert and delete. We're going to assume we have all the points we're interested in and then build the data structure around that. We're not going to handle polygons, only points, and we'll just do a basic construction strategy. Yeah?
And the real R tree would handle all these points?
Yes, a real R tree takes care of all these problems. Okay, so first some intuition around what an R tree does and why is it built the way that it is and what data does it hold. It's going to come down to the idea of a bounding box. So if I take some small set of points, these 4 black points here, I can draw a box around them, a minimally bounding box. So the edges of the perimeter of this box is exactly as small as it could possibly be, at least if it's axis aligned. You could maybe rotate the box to get it a little smaller, but that makes it a lot harder. And then the intuition here is that if the red point X is the point I'm interested in, I can easily calculate the distance between X and the box, and then that tells me that the distance between X and any point inside the box is greater than D. So, right, if I have to go D just to get to the box, then I have to go further than D to get to anything inside the box. Okay? So if that is D, then all of these distances are guaranteed greater than D. Or greater than or equal. It might be right on the boundary of the box. Okay? Then, kind of using that same idea, we can make a hierarchy of boxes. If the distance between X and some box is D, then the distance between X and any box contained inside that bigger box is greater than or equal to D. And so the distance between X and the top blue box and X and the lower blue box is both greater than the distance between X and the green box. And by extension, greater than the distance to any point inside those boxes is greater than the distance to the green box. So this let's look at what this tells us. I can check for the distance, say I'm looking for anything within a certain distance. I can check the distance between X and the green box. If that is outside the range I'm interested in, then I don't have to look at any of those points. If it is in the range that I'm interested in, then I can look at both blue boxes. I have 2 more comparisons to do. If one of them is outside the range I'm interested in, then I can cut out half of the points. And I do then still have to go look at the other half. So this is essentially binary, it's turning into something like binary search for spatial data, where I have a box that contains 2 boxes inside of it. Each of those boxes could contain 2 boxes inside of them. And this turns into a tree. The green box would be the root node. Its children would be the 2 blue boxes. So it is a tree, but instead of holding like keys or whatever, it holds boxes. Yes?
And the boxes in turn hold more boxes, and it gets more specific until you get boxes that hold only 1 point.
Right, so down at the bottom, at some point there's going to be a leaf node. In this example, my leaf nodes hold 4 points. You can define that. You could say a leaf node should only hold 1 point, or 2, or 10, or whatever. Yes?
How do we determine how to draw that?
Okay, how do we determine how to draw that? That is a hard problem to solve that is actually still being worked on. There are good options. We are going to look at a very simple option, and it works because some of those simplifications that I mentioned a few slides ago. So here are all of the points we're ever going to deal with. We'll never insert or delete any of them. That's part of what's going to make this easy. So how do we build this data structure? We start by drawing a root node box that minimally bounds every point. So that would go something like this. Okay. So that now is the root node of the tree, and it holds information to represent this box. Then I'll switch colors to get to, come on, how do I switch colors? Okay, maybe I won't switch colors. Then we have to decide how do we make the children of this box. There are lots of different possibilities. Like maybe I pick just these two, and that's one child, and then all the rest of them would be the other child. The goal is you want to minimize overlap, and you kind of want to minimize empty space. There are algorithms for doing that. We're going to do something pretty simple, and basically what we're going to do is just split them roughly in two based on the median. So we will pick one dimension here. We'll pick the x dimension, sort all of the points on the x dimension, and then split in the middle. So there are 10 points total here. That means we'll get 5 in the left one and 5 in the right one. And if I'm sorting on the x dimension, then we will end up with these 5 points in one box and these 5 points in the other. Okay? So my tree now looks like this. I have this big root node. The left child is this kind of smaller, taller box, and the right child is this bigger. So it's like this is the left child, this is the right child, the whole thing is the root. Okay? Yeah.
You always subdivide it into two.
If in a binary tree, you always subdivide into two, but in an R tree, since you want to fill up pages more efficiently, the branching factor is going to be wider. And then we keep going. So one simple way to keep doing this, we don't want to split on the x dimension again, because then we'll end up with really tall, narrow boxes. So for the second level down in the tree, we split on the y dimension. So for each of these two children, I'm going to now split roughly in half in y. So I would get that and that. And this and this. Okay. And then let's say that my stopping point is when a leaf node contains 3 or less points. So this is our tree. Okay. So drawn slightly better and with color coding. That's basically the tree we just drew. Okay. Now, the kind of question we might want to ask. Let's do KNin. So let's say that the point I'm interested in is this x, and I want to find the k nearest neighbors of x. So the algorithm it uses a priority queue. We enqueue the root node into a priority queue, and the priority of nodes that we enqueue is going to be the distance from x to the node. So let's call this is A, the root node, this big blue box. So here's our priority queue. It contains the root node with a priority of 0. The reason it's 0 is because x is inside the box. So if x is inside the box, then we call it a distance of 0. Okay, and then we pop the queue and enqueue both of its children with their distances. So we'll pop that, and the children of that root node are, we'll call this B and C, the two green boxes. So we enqueue B with its distance from x. So let's call that 4. I'm going to just make that up. That's 4 units. The distance from x to the C box is 0 because it's inside that box. So we're actually, since this is a priority queue, we're going to have C on there first with 0, and then B with 4. And then keep going. Pull a node off of the priority queue, and then enqueue its two children with their distances. Okay, so I'm going to pull off C, and I'm going to add its two children. So let's say this is D, and this is E, those two red boxes. If I'll have to kind of just make up some distances here. Let's say this distance to D is 1. Distance to E is 1.5. It is a little larger. So we'll get D first. It actually goes in front of the B, which had a priority of 4. So we put in D, 1, E, 1.5. B is still in there with 4. So B is going to be popped much, much later because it's so far away. This is getting us to the points that are close first because it's priority on distance. Okay, so now we're going to pop D. D, turns out, is a leaf node, so we kind of just enqueue. We figure out the distance from x to its 2 points and enqueue them. So if I say this is F, this point is F, and this point is G. Let's say F has a distance of maybe 1.2, and G has a distance of, I don't know, 2. So I'm going to put F onto the queue with a priority of 1.2, which will put it in front of E. And since that is a point, as soon as I pop the F off of the priority queue, I can put it into my nearest neighbors in order. So F is my first nearest neighbor. And then you just keep going. The next thing I pop would be E, and I would put in all of its children, those points, into the priority queue, and just keep doing that until your nearest neighbors list contains K. However many K you want, you just do this until you find the K nearest neighbors. Okay? So this is kind of reminiscent of Dijkstra's algorithm, in that it's using a priority queue to visit things in a certain order, and the order is based on distance in this case, just like it is in Dijkstra's.
So it seems like this algorithm would still work if you didn't limit it to 2 or 3 points in the bounding box, but it's more efficient for different values. So was you picking 3 or less sort of arbitrary, or what's the logic behind that?
Me picking 3 in this case was just to keep the diagram simple. If this was the entire thing so let's look at this node E, this big box here. You wouldn't want a leaf node to be some substantial fraction of the size of the root node, you would probably split this down further. But it's such a small example that you just can't really see it. In a database, the size of a leaf node is going to be more importantly determined by page size rather than keeping the tree structure really good. Data structures like this, when used, so these are used in all over the place, not just in databases. These are used in physics, collision detection, graphics. Not exactly this data structure, but data structures like this. And in those cases, you usually want to split down to pretty small leaves, like 2 or 3 things per leaf. Yeah.
So you're ensuing the box region, and then when you pop it up, you're ensuing the points. When you
pop any node off of the queue, you enqueue its children. So if its children are boxes, then you enqueue the boxes. If its children are points, then you enqueue the points. Okay. So I wanted to draw it just to kind of walk through it more clearly, but I've got kind of the same process on slides. So we make a priority queue. We start with the root node. We go forward. So this way you can kind of watch the priority queue grow and shrink. And as we pull items, as we pull points off of the queue, those are the nearest neighbors. And we just keep going until we have found k of them.
So the priority of the boxes is how near it is to x?
Yes, the priority is the distance from x. And distance from x is considered 0 if x is inside of a box. Okay, so the real data structure for this, what I kind of showed here is kind of an R tree. The real R tree, it's called an R tree because it's a rectangle tree. It holds rectangles. It has a much wider branching factor to deal with page access better. And it's always balanced, even though it can it can handle arbitrary insertions and deletions. It was easy to make our tree because I knew all of the points ahead of time. So it has the same kind of issues where it has to occasionally split and merge nodes. And doing that in an R tree is a lot harder than doing it in a B+ tree because there's not necessarily a good answer for how do you want to split these boxes. It's going to be based on a heuristic, and you're never going to get the perfect answer. Okay, so dealing with spatial data in SQL, I talked about those 3 types: point, polygon, line string. So let's say I want to make a database of fast food chains, or fast food actual locations. So it has like a name, the name of the place or whatever, and then a location. So in our example, location is just a 2D point. So it's not really an address, but in Salt Lake it is, because we just have grid addresses. So if my x is 400 and my y is -255, that would be like 4th east and 255 south. Okay? Points are kind of stored in a binary form, so if you just do like select location from this table, it'll just give you a bunch of gibberish. But you can use as text to convert it into something readable. And then when we want to actually create a point, so kind of like creating a date, you use the date function and then put the date you want. To create a point, you just put in two numbers into this point function, and that'll construct a point. Okay, and then finally, the kinds of operations we can do on this. We'll just look at one. st distance just returns so straight line distance between P1 and P2. So like square root of x squared plus y squared. So if I want to know the distance from like the origin of downtown to any other fast food chain, I can just make a new point at the origin with whatever the location is and select the whole thing out of that table. So let's go over to this database I have called cities. And actually the only thing in there is fast food. But you can imagine maybe I have hospitals or some other tables in there as well. If I select star from fast food, so I get the names of a bunch of places, and then points are binary, so it can't really display them. But I can do select name and as text location. Okay, so these are actually real places around Salt Lake, at least as of about a year ago. Some of them may have closed up, but so this one, this means 100 east, 28 south. So positive would be north, negative would be south in the the first coordinate. Positive is east, negative is west in the second coordinate. Sorry, in the first coordinate. So this one here is like 18 west, 100 south. Okay. So if I want to know the distance, so I'll do select name, comma, st distance. If I want to know the distance from the origin for all of these things, make a new point at 0, 0, and then just the difference between that point and the location pulled out of the table from. Okay, so I get like Jimmy John's is probably the closest one. I think it's like on South Temple or something. So this is just straight line distance between all of those. So if I wanted to find like the nearest ones, then I can just do order by. Now here's an issue. Look at the name of the st distance column. I would have to do order by st distance, all of that. So I'm going to name it instead. I'll call it as distance. And then I can order by distance. Okay, so closest one is Jimmy John's, then Subway, then Chick-fil-A, and so on. This is basically, let me refine this a little bit, limit 2, something like that. Okay, that is basically KNin, where K is 2. I want to find the 2 closest things to some point. Let's use our location. So we're on something like 1400 east, first south. That road right there that comes up here is first south. So now the closest ones to us are that McDonald's down on like 7th East. I've eaten there as recently as 2 days ago. Don't judge me. I know that one is still there. So this is essentially a KNin. You don't, the way you specify it is not something like do a KNin search on this point. It's more along the lines of like SQL syntax, where you use order by and limit and things like that. So this would turn into a KNin search. Okay, so that works regardless of whether you have an index on this spatial data or not. It's just SQL is gonna run the query in a slow way if you don't have an index. To create an index, it's create spatial index. So kind of slightly different syntax, but instead of creating a B tree, it'll create an R tree. Except InnoDB actually doesn't support R trees, unfortunately. MySQL does, but the underlying engine, InnoDB, that MySQL is using does not. So if I tried, these KNin queries I'm doing here are actually kind of just brute force. They're expensive, and it works fine because I only have like 10 things in here. If this database got larger, it would start to get very slow.
So we tried to
if you tried to create a spatial index on something that's one-dimensional, it would either, I'm not sure, it would probably just turn it into a B tree. Yeah.
So with NODB, you're likely just taking the spatial location and disguising it as a more efficient algorithm to run this class?
So with NODB, I'm what?
Taking the spatial table and disguising these operations as a more efficient algorithm for demonstration.
I'm not disguising them as a faster implementation. This is a slow, unoptimized search because I don't have an index on this table. Does that answer your question? Okay. Yep.
So, what is the point data type? Yeah, point data type of the spatial index. Or are there other types on the column?
So yeah, you can use other types like polygon. You can make a spatial index on the polygon type or the line string type. Those three plus I think there are a couple others, various other geometries.
So this was actually a question about the polygons. It seems relevant to bounding boxes. Seeing that bounding boxes are technically themselves polygons, how exactly does the computer determine the distance between the bounding boxes and their polygons at X?
Right, so how do you find the distance between a polygon and a point?
Yeah.
That's a more expensive operation. It's easy with a point. With a polygon, it depends on the shape of the polygon. You have to, basically find the closest point on the polygon. There are ways to, speed that up, but the tree itself is still an R tree. It still contains rectangles, but instead of finding the minimum bounding rectangle for a bunch of points, you have to find the minimum bounding rectangle for a bunch of polygons. Yeah.
Does any database natively support more than 2 dimensions for these spatial indexes?
Yeah, so you can go up to, you can increase the dimensionality of this, and then it becomes a bounding volume instead of a bounding square, a bounding rectangle. Does the database support that? I don't know. But in something like computer graphics or collision detection, you're obviously dealing with 3D most of the time. And so it looks like this, except three-dimensional. Yeah.
So what about more than 3 dimensions?
You basically, the only difference is in how you compute these minimum bounding volumes. For every dimension, you have to find the min and the max. That's how you compute the bounding volume. So you take a set of x things, n things. To compute the 2D bounding box, you find the minimum in x and maximum in x, and then minimum in y and maximum in y. That's your bounding box. For more dimensions, you just do it for z and t and any other dimension you have. Okay, that's it for today.